So welcome to another season of Saturday Physics. And we have a very exciting lineup this year. So you hear talks on seeing the quantum world in the atomic scale. You'll hear talks about listening to the black hole merger, billions of light years away. And to kickstart the season, we have Professor John Thaler. And Professor Thaler got his PhD at Columbia University. After teaching at Princeton University, he came to the department at 1977, and he's been here ever since. He's an expert in both particle physics and astrophysics. So in recent years, people have found there's very intricate connections between fundamental particles and cosmology. So Professor Thaler is a pioneer in this area. So he's going to tell us something very exciting today, exoplanets. You actually probably heard about them in news. They are in news a lot. And very recently, people found an exoplanet at Proxima Centauri. It's only 4 light years away, so it's maybe possible for us to visit. So you may have a lot of questions about them, what they are, and what the discovery means to us. And if you have questions, you have come to the right place. So let's welcome Professor John Thaler.
Okay, so before we get started, I just want to mention the study of exoplanets is a very complicated and difficult subject, but apparently not as difficult as getting the display to fit on the screen. So the ones on the side are, so some of the text may disappear off the side of the screen, so look at the side displays. Anyhow, so we will be talking about exoplanets. What I'm going to do is describe what is an exoplanet and why are they interesting. And then, so that'll be sort of a preamble. Then I'll spend most of the time actually talking about how we actually look for them. And the last third of the talk or so will be a discussion of the one that was recently seen. And in case you're wondering, actually I agreed to give this talk before the planet was discovered, so it's a complete coincidence that there was a new discovery, which of course makes this talk much more interesting. So anyhow, so an exoplanet, if you look out in the sky at night, mostly what you see are stars. You see there are a few planets you can see, but most of the bright objects you see are stars. You can see a couple galaxies, but they're fairly faint and they're fuzzy blobs. We won't be talking about them. In fact, we won't be talking about any cosmology at all. So this is a little bit out of my field, but I think I can give it a reasonable talk. So one of the issues actually, if you see a star with something orbiting around it, how do you know it's not a binary star? I'll talk about that a little bit. That is, how do you tell that it's a planet orbiting a star, not two stars? Because binary stars are actually quite common. One of the answers to that question is stars are all much heavier than planets. The lightest star is about 70 times as heavy as Jupiter. So if you see something that's Jupiter size or smaller, it's got to be a planet. It can't be a star. Otherwise, the center doesn't get hot enough for the fusion to occur. The fusion is what produces the light, the heat and the light. And so we take advantage of the fact, among other things, that planets don't emit light, and we'll see that later in the talk. So that's how we tell that we're looking at a planet. Low mass and no light. Low mass mean compared with stars. Okay. So, but we'll revisit these issues. So why are they interesting? Well, in terms of life, around every star, if you have an object that's near a star, well, let me back up a little bit. I have a little preamble here. I'm not going to talk at all about the formation of stellar systems. That's a very complicated and controversial topic. And what the main thing is that it's going to make a lot of what I say a little squishy because we don't really know the answers to a lot of the questions. In fact, that's one of the important points I want to make here, is that we really don't know all the answers. And I'll describe why that is in a lot of situations. But I'm not going to talk about it in detail. Planets come in two types. There are big planets like Jupiter's that are big balls of gas, mostly hydrogen. And there are small objects that are mostly rock, things like Earth. And that's one of the things we want to understand. When we see a planet, we want to be able to distinguish these two kinds of objects because we're looking for objects that can support life as we know it. I'm not going to discuss other possibilities for other life forms. Sounds like there's a tornado coming. I hope not. Anyhow, so I'm just going to, in which case we're looking for rocks. We're looking for Earth-like planets that are also in a distance from the star such that you can have water, because we know our kind of life requires water. So for a given star, if you're really close to a star, it's too hot. If you're really far away from the star, that's like Mercury or Venus. If you're really far away, like Pluto, which is no longer a planet, but nevertheless, it's cold. And so there is a region called the habitable region, and planets that are in that region that could have liquid water and therefore could support life are called Goldilocks planets. Yes?
So we're excluding the possibility of a moon orbiting a planet having its own life.
We aren't capable at this time of seeing such objects, so I'm not going to talk about them. Right? Yes?
Could gas giants exist closer to their sun, or they're always in the same relative?
Oh no, in fact I'll show you a picture later on in the talk. Actually, most of the gas giants that we have seen are actually fairly close to their star.
So ours is an anomaly?
We don't know. It appears we've only seen a few thousand, and so we haven't built up enough statistics. And the other thing is the methods we use, and I'll talk about that a little more, bias our sensitivity. We are not sensitive to planet various orbital configurations, and I'll describe why that is. Right, so the sample that we've seen isn't necessarily representative of what's actually out there.
One more question.
Yeah.
What's stopping there from being a gas dwarf instead of
I'm sorry, say it again?
What's stopping there from being a gas dwarf instead of a gas giant?
Oh, there is a small... I'll talk about that too a little bit. There are gas giants that can be smaller than Jupiter. And so we will see that. If it's really too small, then it's going to be a rock and not a gas giant. But there are gaseous planets that are smaller than Jupiter. We even have 2 of them or 3 of them in our solar system.
I'm thinking more like Earth size.
No, you're not going to have a gas giant that's the size of the Earth. And actually, we can tell that there are ways of distinguishing gas from rocks, mostly by the density. There was another hand up? No, I thought I saw one. Okay. Right, so that's what we're looking for. So a bright, hot star has a habitable region that's a little farther away. This is a star like Sirius, which is a big, bright star. A star like the Sun has a habitable region that's a little closer. And a cooler star, a red dwarf, will have a habitable region that's closer in because it's not so bright. Okay? So that's why they're called Goldilocks planets. Not too hot, not too cold. So, how do we find them? So there are several ways of doing it, but the primary reasons, there are 2 primary methods that we use to find planets. One is what's called the Wobble method, and I'll talk about that more. Basically, as the planet goes around, the star recoils a little bit, and you measure the motion of the star. You infer the motion of the planet by measuring the motion of the star. And the second is, if a planet happens to go in front of the star, what's called a planetary transit, then the star gets a little dimmer because the planet's blocking out the light. Okay, and so what you see is a periodic blocking of the dimming of the star. Okay, most planets have been seen that way, and those are the ones I'll discuss. In principle, we'd like to observe a planet both ways in order to determine its properties more accurately. Yeah?
So reflected light off of a planet really isn't bright enough to be detected?
No, they have been, a few planets have been seen that way, but not enough. I'm not going to talk about it. Okay, if you want, I can show you some pictures afterwards. Maybe at most a handful have been seen that way. That's a promising technique for the future, but our optical techniques are just now becoming good enough to see them that way. The problem is a planet's not very bright, and you've got this really bright object right near it. So somehow you have to block off the light to see the dim object near the bright object. That's difficult.
So you'll only see a transit if the orbit is...
That's right. So only a small fraction of planets out there will have the right alignment that it passes right in front. Just like we don't get eclipses every month because the orbits aren't aligned. Right. Okay. So let me talk about the Wobble method. Basically, when two objects are orbiting each other, the thing that remains stationary is the center of mass. And so I'll make this is a movie. As this planet goes around, the sun in the middle goes in a little circle. It's just like if you've ever swung a bucket of water, you have to lean backwards a little bit because the bucket is going around and you have to balance that bucket's motion. And the ratio of the speeds depends on the ratio of the masses. So that's a way of measuring the mass of the planet, okay, by measuring the speed of the star. So what I'm going to do is show an animation, which I'm making. It's going to be a binary star animation because if it's a planet, the effect is too small to see. And nevertheless, let's see if I can get this to work. Can I get it to work? Yes, there we go. Oh, there we go. For reasons I stole this animation from this guy, and for reason. See, when the planet's moving towards us, it's got a motion. When it's moving sideways, this is the velocity towards or away from us. And so when it's moving away from us, it's got a negative speed. When it's moving sideways, it's got a 0 speed. And now it's moving toward us. So let me stop it.
This is moderately simple with a binary system.
Yeah.
Could a space alien infer our planet when you've got 9 planets around the sun?
The answer is probably yes, because the planets don't affect each other all that much.
But it changes how the sun moves.
Yes. No. In fact, multiple planetary systems have been seen, but then it's not such a nice, simple sine wave. You have a complicated sine wave with several different superposed with the orbital periods of the different planets. That's a doable analysis, but it's more complicated, right? And so, in fact, systems have been seen with 4, 5, 6 planets by this kind of method. It gets more complicated, and sometimes people have spurious, what are called false positives, and so that's why I say we need to be careful about the data. And I'll talk about that a little more too. So anyhow, so what we've got here then is, this is the motion of a binary star orbiting around the sun in an Earth-like radius. So I said, let's suppose there's a star that has about 13% the mass of the sun orbiting with a 1-year period. And AU is the radius of the Earth's orbit. That's sort of a standard term, so I'll use that term AU. It's the distance from the sun to the Earth. Yeah?
Would you get the same effect of the wobble, like you were using the analogy of a water bucket? If
Yeah.
you had a large water bucket that you were almost holding right onto and you were spinning versus a smaller bucket that was on a roll?
That's right. What'll happen is, if it's close to you, it'll be much faster. If it's farther away, it'll be much slower. So
There is a way to kind of codify. It's not on a sliding rule. It could be this or it could be.
no, that's right. We can tell. We can tell because we know the mass of the star. We understand if we see a star of a certain brightness, we actually know enough about the physics of stars that we know very accurately how massive a star is from its brightness. So if we know the mass of this guy, and therefore we know the period because the length of the year depends on the mass of the sun. So the length of the year tells us its distance, and therefore we get the mass of the planet. So there is enough information. The thing we don't, actually there's one unknown, which is we don't know that we're looking at the orbit straight on. It could be at an angle, and there is some uncertainty due to the angle, the tilt of the orbit. Right, but I'm going to ignore that. Right. So if it were a binary star, the sun would be moving several kilometers per second, 4 kilometers per second, if we were an observer way over here. And similarly away from us at 4 kilometers per second. So that would be easy to do. The problem, though, is that planets are much less massive. The Jupiter is only 0.1% the mass of the Sun, and the Earth is only 3/1,000,000th the mass of the Sun. So the effect is much smaller, because the Sun is hard. The motion of the Sun is really tiny, because the mass of the planet is really small. In fact, if you calculate it, the sun's speed due to Jupiter's orbit is about 25 miles an hour, 12 meters per second. The sun's speed due to the Earth's motion is about 1 mile an hour, 8 centimeters per second. So I can move my hand as fast as the sun is moving due to the Earth's orbiting. That's really small speed, okay? Fortunately, though, we can actually measure speeds on this order, and I'll talk about that using the Doppler effect. So I can spend some time talking about the Doppler effect. When the sun, you all probably have heard about the Doppler effect, right? When a car is coming toward us, the pitch of the sound is higher frequency. When the car is moving away from us, the pitch is lower. The same thing happens with light. When a star is moving toward us, the frequency of the light is higher, which makes it blue. When it's moving away from us, the frequency is lower, which makes it red. So that's how we tell the speed. Let me just show you the video here. I hope the sound isn't too loud. All right, so there's a car with his horn blaring at a certain pitch. He's coming toward us. As soon as he goes away, now the pitch is lower, and we can measure the speed. That's how the police catch you. That's right. All right, so that's how the police catch you. I estimated those frequencies. In fact, the last time I gave this talk, there was somebody in the audience who had perfect pitch and said, "No, you got the frequencies wrong." But anyhow, the incoming frequency was about 460 hertz, and outgoing was about 400 hertz, which implies, I'm not going to go through the calculation, that the car was going just over the speed limit. Not enough for a speeding ticket. Anyhow, light, as I mentioned, light's a wave, and so we can do the same thing with the star. When the star is moving toward us, its light is slightly bluer. When it's moving away, it's slightly redder. And unfortunately, the speed of light is so big that we're talking about tiny effects. We need to be able to measure the frequency to 3 parts per billion if it's going 1 mile an hour. Okay? 1 meter per second, which is about 2 miles an hour. That's the kinds of speeds we need to be able to measure in order to detect the orbital motion of these planets. Fortunately, I'm not going to go into it in any detail. Optical techniques are actually capable of this kind of accuracy. Okay, so you'll just have to trust me on that. I'll show you some data, and you'll see that, in fact, it's true.
You would have to factor out the motion of the Earth in our orbit, too, wouldn't you?
That's true, but we know the motion of the Earth, so that's a correctable effect, right? Right. In fact, a lot of astronomical measurements we have to correct for the motion of the Earth. So let's look at some data. Okay, so here, this is real data. This is not an Earth-like planet. This is a Jupiter-like planet orbiting a star about 60 light years away. In fact, this planet is very nearly the same mass as Jupiter, and the star is only slightly smaller than the Sun. It's about a the period is about 9 years, which is not that much different from Jupiter. That's because this planet's a little closer to its star than our Jupiter is to our Sun. So it has a shorter year. Okay? So, in fact, here's the data. We are looking at a star 60 light years away. If there were an astronomer out there looking at our solar system, he could see our Jupiter with data like this, because it's a very similar situation. So that's how they could detect us. Okay, using technology that we have. Okay, and here you can see the effect of the accuracy of the measurements. This measurement, the uncertainty in each of the speed measurements is about 2 meters per second. Okay, that means we're going to have difficulty measuring speeds that are smaller than a couple meters per second, because our measurements just aren't accurate enough. Okay, and I'll show you what that means. That means it's difficult to find small planets with this method, unless they are very close to the star, because then it's going really fast. Okay? So if you want to look for Earth-like planets are more easily found if they're close to their star, because they're zipping around faster. All right, that's what I said. That's why I said our observation of planets is a biased selection, because we're more sensitive to planets in certain configurations. Yeah?
Okay, I'm confused. If you have our sun, and we have multiple planets.
Right.
Okay, so and the sun is pulling away from each planet.
That's right.
Come on, how can you do that?
Well, one thing is, Jupiter is much more massive than any of the others, so its effect is much bigger than any of the others. The other thing is, in fact, I'm not going to go into the details. We can actually, let me back up to that previous, wherever it was. Oh, remember when I showed this thing with the wavy motion? If you have two planets, you now have two waves, probably with different frequencies, because the planets will have different orbits, different years. And so we can do a mathematical analysis of the shape of this curve if there are multiple planets. Let me just pause it there. All I want is the picture. If there are multiple planets, you'll have a more complicated shape to the motion of the star.
But at some point,
But it's possible.
Distinguishable from noise.
That's right. No, I mean, that's why measurement uncertainty limits our ability, and people have made false positive detections because of that kind of problem. But if the planets are big enough that the effect is big enough, we can see multiple star systems just by doing, as I say, a mathematical analysis which tells us that it's a more complicated shape. But I'm not going to get into the details, but that is a straight, if you're technically, if you're an expert, it's a straightforward analysis to look for multiple planets. The limitation is the noise in the measurements, which limits our ability to know exactly what the shape actually is.
Is all of that based on the presupposition that all the planets are coplanar?
No, that's not needed, although what it means is that we won't know the masses of the planets so accurately, but we will be able to detect the planets. That's right. That would still, as I say, it will change our estimation for the masses of the planets, but not for the detectability of the planets.
So if you increase the number of planets, does that change the harmonic of the wave, basically?
That's right. That's what it is. I didn't want to use that term because It's a harmonic analysis. It's just like in music. You can tell that there are multiple frequencies if you hear an instrument playing. You can do a spectral analysis and know we have a certain amount of middle C, a certain amount of middle G, a certain amount of the different frequencies. And each of those corresponds to a different planet. Yeah?
The system you've drawn is a nice circular orbit. Is it true that most of the planetary orbits are circular, or what about
Planet, if it's not circular, then the shape of the curve will be a little different, which I'm not, again, that's a calculable quantity. And so you have to take that into account. That's right, but most orbits are actually close to being, most planetary orbits seem to be close to being circular. Oh, so where was I? Oh, here we go. Anyhow, so this is how we can discover a Jupiter, or how they could discover our Jupiter. And all right, so the point is that we have a measurement accuracy which is not good enough to see the Earth. Here's some more data. This is closer to being an Earth. This is a planet with a mass approximately 4 times that of the Earth. The reason we can see it is that it has a 20-hour year. It's really close to its star. And so it's really whipping around quickly. In fact, it's only, remember, 1%, an astronomical unit is 93 million miles. So we're talking about a planet that's less than 2 million miles from its star. A 20-hour period. It's called Kepler B. I'll talk about it a little bit more later. But because it's so close to the star, even though it's an Earth-sized planet, it's way too hot to be habitable. Okay, so this is not a life candidate, but it is an Earth. Okay, this, in fact, as I recall, was well, I'll get to it. I think it may have been the first Earth-like planet found.
Excuse me, what makes it Earth-like?
Because it's small, and the size? Right. At the moment, we know the size. No, we don't know its size. We know its mass.
But
that's right.
The same mass.
That's right.
Okay,
That's right. I'll tell you how we get sizes of planets too. That's the other method. Okay, but you can see the main reason I wanted to show this is, see, the effect is smaller. This guy is only moving, the star is only moving towards us at 4 meters per second and away from us at 3 or 4 meters per second. This is a noisy signal, and in fact, if I got rid of 3 of the measurements, there wouldn't be any signal at all. This is really a marginal detection of a planet. Okay, and as for lower mass planets, you can see it would be even shakier to claim that you've seen anything. In fact, this planet was not discovered by this method. It was discovered by the other one, which I'll talk about, because it's too noisy a signal for us to have claimed a discovery with this data. Okay, so here's a plot of planets discovered by the Wobble method, and the important thing is I drew some lines. Let me explain. So here's the radius of the orbit. Here's the Earth at 1 astronomical unit. The mass is in terms of Jupiter masses, so there's 1 Jupiter mass. So there's the blue dots are our solar system. There's Jupiter. The effect of Jupiter on the sun is bigger than a few meters per second. So this is everything above this line we could see if our measurement accuracy is 5 meters per second. We could see Jupiter. This is what you could see if the measurement accuracy is 1 meter per second, which is a little bit better than we can do right now. The Earth is down here at 8 centimeters per second. So that's why we can't find Earth in an Earth-like orbit, because not by this method. The Wobble method, the star is moving too slowly for us to be able to measure. Okay, so we could see Jupiter. With our accuracy, we can probably see Saturn. This is Uranus and We would not be able to see them from out there, because even a fairly big planet like them doesn't cause a big enough effect. Remember, the farther away they are from the star, the smaller the effect. That's why we want to see stuff close in. Okay, so we can see a lighter planet, the lighter the planet is, the closer in it has to be. Here's that Kepler planet. It's just marginally visible by the Wobble method. Its star is moving a couple meters per second.
So those others are Mercury, Venus, and Mars?
That's right. That's Mercury, Venus, Earth, Mars. Right. Okay, so here's what we would see. If you wanted to find an Earth, here's the effect. The sun moves 8 centimeters per second due to the Earth's orbit, so this is the signal you would expect to see with a peak of plus 8 centimeters per second and minus 8 centimeters per second. If you put simulated data on there with a 1 meter per second resolution, that's what your data looks like. There's no way we're going to see that curve with that kind of data. We need at least a factor of 10 or more improvement in resolution, which may be possible, but not now. Okay, so let's look at the other method, what are called planetary transits. When a planet passes in front of the star gets a little dimmer because the planet's blocking the light. And the amount is just a matter of how much area is the star. Okay, so it depends on the square or the radius of the star. So the radius of this, and it depends what fraction. So the sun, the radius of Jupiter is about 10% the radius of the sun, so the sun would get dimmed by 1% as Jupiter passes in front of it. That never happens in our solar system because Jupiter's orbit is outside of ours. We only get transits of Venus and Mercury. The Earth, though, is only 1% the size of the sun, so its dimming is tiny, a 100th of a percent. Okay? I'll show you some data, but just for historical, well, maybe, okay, I have time, right? You don't mind if this is a 2-hour lecture, 3-hour lecture, fine. I figured you'd like that. So here is for historical. This is the first movie ever made in retrospect. This is photographs of Venus traveling in front of the sun in 1882. What it is it's a movie. The movie was only made about 10 years ago. It's a composite of a whole bunch of still images that were taken at the time. Photography was still a fairly new technology then, but they took photographs of Venus, and there it was. If you want to look it up, it's on the YouTube.
I have a question about that. So two questions. One is they must have used a filter.
Say it again?
They used a filter to take those photographs. They had to use a filter, right?
Oh, sure, probably.
And my other question is that the earliest, or was there a time before when they were able to detect things like this? Like that they had the equipment or possibility to detect it?
Well, the right answer is I don't know. Okay. But my guess is they probably didn't. Transits of Venus don't happen very often, only about once a century. So this was probably the first time they had an opportunity to take this kind of picture. All right, so let's look at transits of Venus. This is what we expect. Suppose Jupiter did pass in front of the sun. You would expect to see this kind of data every time Jupiter passed in front of the sun, if you were looking at it from some distance away. You need, right, so it's going down by about 1%, down to 0.99. So you would like 10th of a percent accuracy. That's what this data shows. So this would be really strong evidence for Jupiter passing in front of the sun if you were looking at the sun from some distant place. If you do the Earth you need, since the sun is only going down, its brightness is only dimming by 10 to the minus 5. That's a tiny dimming. We can't do this is good enough. We can make measurements of this accuracy on individual images. We can't make this kind of accuracy on individual images. Oh, this is a dual color laser. Wow. So what you have to do is, you can only get this kind of accuracy by averaging lots of measurements. If each measurement is certain accuracy and you take 100 of them, then your average, you can get the average better. That requires that you have many orbits, which means you need a short, again, the planets need to be close to the star so that you can watch it go around lots of times and average these measurements over many, many periods. Okay, so again, we are biased towards planets that are close to the star. Okay? Anyhow, so that requires, as I say, that requires short period orbits. A planet needs to be close. Okay, so as I say, our sample of planets is not unbiased. So we don't, it's very difficult to learn what the actual distribution of planets around stars is. It's an important question, but it's not an easy one to answer. All right, so here's one of, I'm not going to talk in detail about it, but I want to show a picture. Most of the planets that we have found have been made by Kepler, which is an orbiting telescope. It doesn't look quite like the Hubble telescope, but it's a similar object. It's a telescope. It's a CCD camera, which is located inside here. These are the CCDs. Very same kind of thing that's in your pocket camera, right? Of course, they do things to make them more sensitive, but basically it's the same. It's just a CCD camera that's been optimized to make very accurate measurements. Right. You may all know, maybe not. It was launched in 2009 and found lots of stars. Basically, it continuously monitors 100,000 stars and waits for signs of the dimmings of the stars. Okay, and it's found several thousand. Its gyroscopes failed. That's a common problem for space telescopes. Mechanical systems don't work very well out in space. I won't go into it. Gyroscopes tend to fail. They failed in 2013. It still works, but with reduced capability. 2 successors, one by NASA and one by the European Space Agency, will be launched next year to continue this kind of project. So here's some data. It has found most of the planets, because big planets block out more light, it's easier to find them. Most of the planets found have been gas giants like Jupiter's, but a few are rocky like the Earth. So I'm showing 2 data. So this is the Kepler 10b discovery. This is how this planet was discovered, not by the Wobble method. Because, excuse me, because too small. Right? Here's a bigger planet that has a bigger dip. It's what I would call a Neptune. It's smaller than Jupiter, but it's still a gas giant. It has an orbital, it's fairly close to the star, but not that close. It's not that much different from Mercury. Okay? And its radius is twice the radius of the Earth. Okay, so it's a little too big to be a rocky planet. So it's probably a mini gas giant. This is Kepler 10b. You can see it's much smaller, the dimming is much less, and this is the averaging of a whole bunch of periods of its orbit, which we can do because its orbit, as I mentioned before, is only 20 hours. So you watch it for a month, you've got lots of samples, and you can average them, and then you can see the signal. Okay, as I mentioned, it's very close. Now I showed one thing, the light. This is what happens when the planet goes behind the star. Nothing happens because it's not blocking any light. When it goes in front of the star, it blocks the light. The reason for me showing that is that's how you tell binary stars from planets. Because the reason why there's no dimming here is that the planet doesn't emit any light, so you don't lose any light when the planet goes behind the star. If you have a binary star, that's not true. here are the typical signals from binary star systems. If you have a big star and a little star, when the little star goes in front of the big star, you get some dimming. When it goes behind, you also get some dimming because it disappears also. So you get this double bump thing. The two bumps are not usually the same because the stars are not usually the same temperature. So you can distinguish planets from binary stars by this observation. Oh, thank you. Yeah.
If the two dips from the stars are very similar, could
Yeah.
that be mistaken for a planet then?
Yes, except that in that case, the two stars are similar size, and then the dips are huge.
Okay.
Right. So in principle, that's a problem, but in practice, it isn't, because then you would have to be a huge planet that's as big as the star, which doesn't happen.
Questions over here.
Yeah.
What if there's a triple star system, like where three stars orbiting each other?
Yeah.
If there was an exoplanet that orbited those three stars?
What would it look like with three?
Oh, well, then each planet would give you this pattern, so you'd just take this pattern, shift it over a little bit, maybe take this pattern and superimpose them. That's what you would see. Each planet just gives you an extra pattern of the same sort. Yeah.
What about planets orbiting neutron stars? Would that be any different for detection?
I'm sorry, say it again.
Planets orbiting neutron stars, would it be different to detect planets orbiting neutron stars than planets
A neutron star?
Yeah.
Well, neutron stars don't emit light, so we wouldn't be able to see any of this.
They actually do emit radar.
Yeah, but okay. The neutron star, we can talk about it later, but the short answer is the stuff that neutron stars emit is beamed very strongly, and we wouldn't see this kind of phenomenon at all. But we can talk about it more later if you come down. So anyhow, so that's the transit method. All right, so let me talk now about what's new. What's new is, a couple weeks ago, an Earth-like planet candidate, and I wanted to emphasize the word candidate because here's the data. It looks like there's a planet there, but it needs confirmation. Okay? Nevertheless, one thing I want to point out is Kepler is an orbiting observatory. In order to measure the brightness of a star very accurately, you need to be above the atmosphere, because the atmosphere makes stars twinkle, and it's very hard to measure variations in their brightness. You need to be above the atmosphere. But for Doppler shift measurements, you can do that on the ground. It's much easier. The atmosphere doesn't affect the wavelength of the light. So this was actually done by a telescope in Chile. I happen to be very fond of telescopes in Chile, but that's another talk. Right, using the Wobble method, and this telescope has actually found 130 planets. The star, Proxima Centauri, is in fact the nearest star to us. It's only a little more than 4 light years away. That makes it interesting because if it really is there, we can study it. It's so close we can think of doing more detailed studies. It's a red dwarf. That is, its mass is only 12% the mass of the Sun, which means its luminosity is only about 1/1000th the mass of the luminosity of the Sun. So that's what we mean by red dwarf. They're cool low mass stars. That means the habitable zone is very close. And as I said, that's where we can see planets when they're close to the star, because our techniques are more sensitive to that. Yeah?
You introduced the discussion of methods by saying ideally we use both, presumably the results of one validates the results of the other. How often are you...
Well, in fact, for this one was seen by the Doppler shift method, which means we would see it even if the orbits aren't lined up. It's estimated that the probability that this is also a transiting planet is about 1%. Okay, that's the probability that the orbits line up well enough that it would be that it would pass right in front of the star. So it's on that order. That's why we don't see very many that do both, because if you see it with one method, the probability of seeing it with the other method is pretty small. Okay? But this planet, it's not much heavier than the Earth, approximately 1.3 Earth masses. Its temperature, that is, if you say, well, we know how bright the star is, so we know how intense the light is that hits the planet. You can calculate how warm it is in thermal equilibrium, and the temperature is below freezing. So the question is, why isn't that too cold? And the answer is, well, it depends. And I'll get to that in a minute. Its orbital radius is close, but that's okay because this isn't a sun, this is a red dwarf. So it's not so bright, which means the planet's not so hot. Okay? If it's real, it'll be very interesting because we'll be able to study it. So, all right, so suppose it really is real. How can we decide whether it's likely to have life? Okay, well, we need to know more about it than its mass. As I mentioned before in the answer to some question, we're just now beginning to image exoplanets. But we can actually learn something about these planets even before we can image them. It'll be nice in 20 or 30 years that when we can get good images, maybe, to do more detailed studies. But that's not for now. Okay, so one of the things I want to mention is if it has an atmosphere, we can determine maybe the atmosphere's chemical composition by measuring the absorption of light that passes through it. So I want to spend some time on that, and that'll basically be my last point. So the hope is that we can measure the chemical properties of a transiting exoplanet's atmosphere, and that will tell us maybe if there's life on that planet. And that's what I want to talk about. So I need to talk about the absorption of light by gases. So the sun emits light. Here's the spectrum of the sun, this nice smooth curve, as it approaches the Earth. And that spectrum is determined by the sun's temperature, 5,800 Kelvin. It's pretty hot, a typical star. But the important thing is it's sort of a nice smooth spectrum. But by the time it gets to the surface of the Earth, it's passed through the atmosphere, and two things have happened. A lot of the blue light is missing. This is the blue end of the spectrum. This is the red end of the spectrum. See, there's a lot of blue light missing. But the important thing for our point of view is that there are particular wavelengths that get absorbed by the molecules in the atmosphere. Okay, so for example, oxygen absorbs right here, water absorbs right here, there's carbon dioxide over here. And you can tell the composition of the atmosphere by looking at these absorption, where the light gets absorbed. Okay? So what does that have to do with exoplanets? Well, if the exoplanet passes in front of the star, then some of the light that gets to us passes through the planet's atmosphere. So if we compare the colors of the starlight when the planet is there to what the color looks like when the planet is not there, we can tell how much was absorbed by the planet's atmosphere, if it has one. Okay? Now that sounds pretty iffy. I will try to persuade you that in fact it's a real practical technique. So first off, here's some gases. So here's carbon monoxide. Carbon monoxide absorbs at about 5 microns. So how can we tell carbon monoxide from nitrous oxide, which also absorbs near 5 microns? And the answer is nitrous oxide also absorbs at 8. So you look at all of the absorption features and you can disentangle what the chemical composition is. Here is some real data. This is real data from 3 planets of the absorption spectra. So this is the quiz. Which one of these planets has life? Why? Yeah, well, okay, that's true. So what are those bumps telling us?
Different gases.
Well, let's look at the bumps and see what they're telling us. So this bump is at about 15 microns.
They all have water.
That's right, that's this one. See this one, look at this. This is right just below 8 microns. There's a huge thing here. 8 microns, that's what we're seeing is this edge here. This graph doesn't go far enough over for me to see all this other stuff. But anyhow, so there's water. What's this one? This one is at around 9. There we are. There's only one. That's ozone. Right? So we're looking, this is a planet that has both water and ozone in its atmosphere. These are planets that have only carbon dioxide in their atmosphere. These are 3 of the solar system planets. You can probably guess which ones. So this is what the Earth would look like if somebody far away looked at our atmosphere. And so water is a necessary feature for life, but it's not a sufficient feature for life. However, oxygen is a very reactive element. And the only way you've got oxygen in our atmosphere is that there is plant life on the surface. Okay, so that's a very strong, the existence of this feature is a very strong indicator that there's life on that planet. Okay? Now, so you say, well, gee, I mean, we're measuring things in our own solar system. What about in some other system? And the answer is this principle has already been demonstrated. I can't show you a nice picture because the analysis was too obscure. But anyhow, another telescope in Chile, the VLT, was able to detect carbon monoxide in the atmosphere of a super Jupiter. You need a big planet because you need a lot of atmosphere. Rocky planets are going to be harder to measure because they're smaller and don't have as much air. But nevertheless, in principle, it's doable, and it has been done in at least one system. Okay, the detection of a molecule in the atmosphere of an exoplanet. Okay?
The first boundary between a rocky planet and its atmosphere.
Yeah.
What's the boundary for a gaseous planet and its atmosphere?
It's not so well defined, but we don't care about that. All we care about is that there was absorption and there are these absorption features. Okay? The Webb telescope, which you've probably heard of, which will be launched in a couple years, will do this kind of study for the gas giants, exogas giants. But we aren't yet ready to do this study on rocky planets. But this is something that's coming. Okay? So, I'm sort of out of time. What do we need for life? Well, we probably need air and water. Do we really need Facebook? I don't know. Right. So, I'm not going to go, I don't have time to go through these things in detail, but let me just mention very quickly some of the complications that we want, that there are. So, I already talked about water. One of the problems is the habitable region of stars tends to be dry. And the reason is, if it's warm enough to have liquid water, then during the formation of the planets, the water all evaporates. So in fact, inner parts of solar systems tend to be dry. So what that means is, there has to have been a mechanism to deposit water on the planets after they've been formed. Whether that's possible or not depends on what I would very politely call controversial planetary formation models. One of which is, the question is, how important is Jupiter? Why Jupiter? I'm not going to answer that now. I'll let you think about it. Why is Jupiter important for this? Anyhow, but it's significant that Proxima does not have a Jupiter. So in a lot of these formation models, the planet Proxima b is going to be dry, unless there's some other mechanism to deposit water on the planet. But I'm not going to go into that in detail. There are other issues. Is there an atmosphere? Well, it's not obvious. If there's water, can't the life just live in the oceans? The answer is the atmosphere does more than provide air to breathe. One thing is it warms up the planet, right? You've all heard about the greenhouse effect. That's the reason why this Proxima planet is considered to be in the habitable zone, because if it has an atmosphere, it's warmer than that minus 18 degrees that I mentioned before. The greenhouse effect warms the planets and moves the habitable zone a little farther away from the star. So greenhouse effects are actually important. The air also protects from radiation. So atmospheres are actually probably important for the existence of life. The problem, though, is the solar wind tends to blow away the atmosphere, so you need a magnetic field to protect from the solar wind. That requires that the planet be rotating. This is getting really complicated. Are the planets rotating? The other problem is the star needs to be reasonably stable, and that's a problem for red dwarfs. Red dwarfs tend to be unstable stars. The sun only varies by 0.1% over its solar cycle. The Proxima star, this red dwarf, varies by a factor of 10 to 100 in its emission of ultraviolet and X-rays. That might not be pleasant for life, but that's not obviously a killer.
Are there any formation models that don't have planets rotating?
Yes. That's why I say the models are controversial.
Questions every time.
Yeah.
The planet has a high radiation field like Jupiter.
That's a problem. If the planet itself has a lot of radiation, then that might preclude life also. Yeah. Yeah.
How old's Proxima Centauri? It goes to the.
I'm sorry.
Life needs time to evolve. So
Yeah.
I was just wondering, Proxima Centauri was.
Well, I'm not sure how old the star is, but it's an dwarf planet. Dwarf stars live forever. The Proxima will live for several trillion years. There's plenty of time for life to.
We don't know how old the star is.
I don't know how old that star is. Right. The only way to measure the lifetime of stars is when they're in clusters and you know there are a whole bunch of stars that are all the same age. It's difficult for a star on the main sequence sits there for a long time and you don't know how long it's been on the main sequence.
Well, we're about halfway through.
We're about halfway through. That's right. Yes. That's true, but there's lots. The problem is there's carbon dioxide in planets that don't have life, and so carbon by itself is not an indicator of life.
No, I meant carbon, hydrogen,
Say it again?
I meant carbon, hydrogen, chains.
Oh, yeah, very complicated biological molecules, but again, those are harder. We got to start out with the simple stuff first. Right, yeah.
Can we detect clusters of amino acids?
In principle, but again, we need to start with the simple stuff first, right? I mean, we're just now beginning to detect simple diatomic molecules that only contain 2 atoms. Trying to detect DNA or something like that is going to be a difficult problem. Right. And so I think, right, the last one is tidal locking. Planets that are, the moon is tidally locked to the Earth. It always has the same face facing the Earth. Planets that are near the stars also tend to be tidally locked, like Mercury is. What that means is the planet has a hot side and a cold side. That makes things much nastier for life. It's not entirely clear. People talk about this a lot, whether life can exist on a planet which only has the same side towards the star all the time or not. And that's a problem because the Proxima planet is almost certainly tidally locked to its star. Yeah?
Fairly recently they've seen a star that has some of the characteristics that you're mentioning, the dimming and stuff. However, it does it in such an erratic way that it suggests that it may be artificial. And it might be the building of a Dyson sphere. What are your thoughts on that?
I have none. I'm going to wait to observe some life before I talk about advanced technological life. Right. Anyhow, here's, just to sum up, here's a brief inventory of Goldilocks planets. Here's the newly discovered Proxima. It's very close to the star. The star is very dim. Earth is up here. This is 1 means 1 sol, that's the sun, at a distance of 1 AU. There are some other planets that have been discovered. It's probably, if you discover a planet in the Goldilocks zone, it's more likely, the benign environment is more likely out here. So I think probably this has the advantage of being very close. That's the thing that makes the Proxima one very exciting, because we can study it in detail. But I would say basically that Proxima is, where was it? My conclusion for Proxima is it's not an ideal candidate for a place to look, but it's close and it's not ruled out, so we should study it. Yeah?
Hawking mentioned a means of traveling to Proxima B.
Yeah, there was this recent proposal for accelerating stuff to near the speed of light, but we're talking about, things that weigh milligrams or micrograms. And it's way beyond what is technologically possible at the moment. Yeah. But it's, in principle, this is only 4 light years away. That means it'll only take a few thousand years for stuff to get there. Yeah.
Should we be looking for systems that have Jupiter-sized planets in outer orbits protecting a kind of inner solar system?
That's right. That would be the ideal system.
Yeah, so
but
we don't have detection method yet. We
yeah.
should be recording those for when we can go back and look for
Right. So we haven't seen any systems that look close enough to our solar system that we can say, there's a Jupiter, there's an Earth, and therefore probably that has life. But we're still looking, and we have thousands, and there'll be thousands more, and maybe we'll find one. But one thing is, it needs to be close enough that we can do some more detailed studies. And that's when this guy here is likely to be a habitable planet, but it's 500 light years away. And so it's going to be tough to study. Yeah?
Is it possible to have a giant rocky planet?
No, there's a limit to the size. If you build up rock more and more, eventually the stuff in the middle collapses. So there's a limit to the size of a rocky planet. I may have a graph somewhere on my computer if you want to look at it later. But right, so something that's 10 times the size of the Earth is not a rocky planet. Yeah.
You mentioned that Kepler looks at 100,000 stars.
Yeah.
How much of a cone of the sky is that?
It's a fairly small cone, and it's looking in a particular direction, sort of tangent to the galactic plane, so that we're looking at a lot of stars. And it just sits there and stares, and it looks at all of them at once all the time.
So how do they decide where to point?
It always points the same way.
In future telescopes?
I don't know. I'm not enough an expert to know what's the best place to look. They're looking along one of the arms of the galaxy, just so they see a lot of stars. Yeah?
What percentage of stars that have been studied by whatever method have been found to have exoplanets?
About half. Yeah, the probability a star has planets is very large. Let me just finish, and then I'll take more questions, because people may want to leave. So the future, they're going to be, the bottom line here is basically, this is going to be a long process of search and discovery. We're not yet quite at the point of being able to detect life on other planets. But here's a couple. I mentioned the James Webb Telescope. Just Thursday, NASA launched another probe that will go out and get some asteroid material and bring it back to the Earth. The purpose there is to understand what the conditions were early in the formation of our solar system, to see what the precursors to life might have been. So there's a whole big program. This is just one. There's a bunch. I mentioned the Kepler follow-ups. It's going to be a long road. I don't think we'll discover life soon. But it looks like it's feasible, actually, to see it.
Should we be spending money on a manned mission to Mars, or should we be...
You're asking my own personal opinion? No. I think manned spaceflight in general, it's good for PR and it keeps people interested. but the scientific return has been very small. Anyhow, I think that's all I have to say, but I'm happy to answer questions forever if you come on back.